Hi, welcome back to the channel. In today's video, we're going to look at how to diagonalize a linear transformation. So let's just get started with the problem. So in this problem, we know that the transformation is from R cubed to R cubed. And then we are already given the matrix of transformation relative to what standard basis for R cubed. Right? So what's the standard basis for R cube? I think everyone knows already by now that this is E1, E2, E3, which is basically 1, 0, 0, 0, 1, 0, 0, 0, 1. And this is already the first step in the process. Now, normally the problem will not give you the matrix of transformation. And if you're not given that, you'll be given the transformation itself. And from the transformation itself, you can then get the matrix of transformation relative to the standard basis. But the first step is already done for you. So from here, you have the matrix. So all you need to do now is to diagonalize this matrix. Now let's look at the processes of how to diagonalize a matrix. The first step in the process is to find what we call the characteristic polynomial. So we need to find the characteristic polynomial. And this is basically the determinant of what? So let's say this matrix is A, the matrix of transformation, minus Ti, where I is the identity matrix depending on the dimension of A. So in this case, dimension of A is 3, which is because it's 3 by 3 matrix. So this identity matrix will also be 3 by 3 identity matrix. Now, if you do this correctly, this will now give us the determinant. All you need to do is to subtract T from the diagonal. So 1 minus T, 2, 3, the other one is 1. The diagonals will just be subtracted. T will be subtracted from the diagonals, right? So this is what you have. Okay. Now, we need to find the determinant of this. Now, if you understand the theory of determinants, it's basically we can use any row or any column in this. The general consensus is to use the row or column that is very easy to compute. In this case, all of them look very complicated, so we can just go with the first row. So we'll just go with the first row. So what we do is what? We take the first term, and then we take the determinant of when we close the row and column that first component belongs to. That would give us 1 minus T. So it will be this entries, 1 minus T, 1, 2, 1 minus T. So we find this first. So this is the determinant of this matrix, this 2 by 2 matrix. Then we go to the second term, which is, then we remember that the first term will have positive plus, the next one will have negative, the next one will have positive, and that's how you alternate the signs. So the next one will be minus 2, the determinant of what? Close the row and column that 2 belongs to. That would give us 1, 1, 3, 1 minus T. Then we move to the last one, which is I think that is that is 3, right? So here is 3. Okay, so we have plus 3, the determinant of close the row and column that 3 belongs to. That will give us 1, 1 minus T, 3, 2. All right, perfect. So this is what we have. Now we need to now compute this. So let's go. Let's do a little bit of computation here. So here we have 1 minus T. And what do we have here? The determinant of this is just the diagonals multiplied together minus the other diagonal. So we have 1 minus T squared, then minus 2 times 1, right? So we have 1 minus T times 1 minus T, then minus 2 times 1. Okay, so the next one will be minus 2. Determinant of this would be 1 times 1 minus T, which is 1 minus T, then minus 3 times 1, which is 3. Then lastly, we have 3 multiplied by 3 times 2 times 1, which is 2, then minus 3 times 1 minus T. So we need to quickly simplify this. So make sure at this point you also follow the simplification so that you get a hang of how generally we compute this. So now we need to expand this. This is just 1 minus 2T plus T squared, then minus 2. Then the next one here, we have 1 minus 3, which is minus 2. So we just have minus 2. So let's not forget the 2 here, right? We have minus 2 minus t. Okay. Then lastly, we have 2 minus 3, so that is minus 1. Then minus 3 times minus t. So I'm just simplifying this. So that will give me plus 3t. Okay. So how I got minus 1 is these two, then minus 3 times 1 is minus 3. So we have 2. So here I have 2 minus 3. That will give me minus 1. So now let's simplify further. The simplification, it will take a little bit of time, but you get through it. So just be patient with the process. So 1 minus 2 is just minus 1. So one more step. Then we can take the minus out here. So we have 2 times 2 plus t. Okay. Then lastly, we have 3t minus 1. So we can now expand. 1 times t is t cubed. Is t squared minus 2t minus 1. So I'm just expanding this. I'm using 1 to multiply this. Now I'll use t to multiply this. Next one is minus t times t squared. That's minus t cubed. Then plus 2t plus 1. Then let's expand the rest. We have plus 4. So 2 times 2 is 4. Then plus 2t. Then plus 9t minus 3. So this is what we have. So let's collect like terms. So we have minus t cubed, right? This is the first one, the highest power. Then for the power of t squared, we have t squared here. Where's another? Is there any other t squared? No, no more t squared. So we have plus. Let me double check that. Hope haven't made any mistake. So we have 1 times t is t squared. I think we have another t squared somewhere, right? Which is minus t times minus 2t is plus 2t squared. Yes. So so this is why it's always good to go back and check your calculations to make sure everything is correct. So we now have t squared plus 2t squared. That is 3t squared. Now, what about the next one would be the terms having t in them, which is minus 2t. We have, what else do we have? Plus 2t, right? So what else? I think I need to go through this multiplication again. So we have 1 times t squared, which is t squared, 1 times minus 2t minus 2t, 1 times minus 1, which is minus 1. Then we have minus t times this, which is minus t cubed. Then minus t times minus 2t, that is plus 2t squared. Then minus t times minus 1, that is plus t. So this is plus t. Okay, good. So now let's do the last calculation. So minus 2t plus t, that is minus t. Then we have plus t here, plus 2t here, that is t. Then plus 9t, that is 10t. So just make sure you go through the calculation correctly. Then last one, minus 1 plus 4 minus 3. So that will be 3 minus 3, that will be 0. So this is the only term that we have. Now we need to simplify this thing further. Take minus t out, right? So we'll be left with what? T squared minus 3t minus 10, right? We have this. So now it makes sense. We can just factorize this one as well. So always when you get to this point, you have to factorize, right? So that you can have linear factors multiplying each other to give us this power of 3. Okay, so now that we have this, so we need to factorize t squared minus 3t minus 10, and that's just basically t minus 5 t plus 2. Okay, so you should be comfortable with doing this by now. So how do you quickly do this? We just multiply the coefficient of t squared and the constant term, that will give minus 10. Look for the factors of 10 that when you add together to give minus 3, and that is minus 5 plus 2. Okay, and when you multiply them, it will give you minus 10 as well. So this is how I know that what the factors will be t minus 5, t plus 2. All right, now that we have here, so basically so this is the hardest part of this type of problem. You need to be able to simplify the determinant and as well as factorizing. Now that we have this, the next step 2 will be to find the eigenvalues. Now, eigenvalues are basically the root of this characteristic polynomial. So mainly we are looking for t such that this polynomial will be equal to 0. So that basically means minus t, t minus 5, t plus 2 equal to 0. Now this gives us t equal to 0, t equal to 5, and t equal to minus 2. So these are the three eigenvalues for this particular matrix. Now, what's the next step from here? The next step is to now find the solution to the eigenspaces of these eigenvalues. Right? So let's start with minus 2. When t is minus 2, start with the smallest one. So all you need to do is remember we got the matrix here, right? So let's write the matrix one more time. So the matrix is this. So 1 minus t. So let me make sure that everything is correct. 1 minus t, 2, 3. Then we have 1 minus t, 1, and then we have 3, 2, 1 minus t. Okay, so what we're going to be doing next now is we are going to be substituting these t values into this matrix, and this is actually the coefficient matrix of a homogeneous system comprising of this eigenvalues. So which means that when t is minus 2, what we have is we have 1 minus 2, that is 3, 2, 3. The second row, we are going to have 1 minus 2 again. We have 3 here, and then we have 3 here. So this is the coefficient matrix of a homogeneous system. What this means is we basically have 3x. So think about having your variables x, y, z. This is basically the solution of this homogeneous set. So we have 3 times x plus 2 times y plus 3 times z, and we do this for all the rows of this matrix. So you need to solve this thing simultaneously. The solution set to this particular equation. Now you can play around with this set of equations to actually figure out the solution set. So what I will do is we'll kind of simplify one by one. So let's call this equation 1, 2, and 3. Now we'll try to eliminate one of the variables from this equation. So let's consider equation 1 and 3, and let's eliminate x. So what we'll do is, it basically means that what equation 1 and 3 are actually the same thing, right? So basically these 3 equations effectively becomes equal to 0. We have x plus 3y plus z equal to 0. Okay, so now what we do is basically we multiply the second equation by 3, right? So multiply the second one by 3, and that will give us 3x plus 9y plus 3z equal to 0. Now, once you do this, we just subtract equation 1 from, so let's call this 4 and 5. So subtract 4 from 5, and that would give us 3x minus 3x will be 0. 9y minus 2y, that will be 7y. Then 3z minus 3z, that would be 0. So we have this. Let me just double check this to make sure that everything is in order. So we multiply by 3. Okay, that looks fine. So that gives us that what y is equal to 0. Now, when y is 0, what happens to substitute this y equal to 0 into equation 4? So that would give us 3x plus 0 plus 3z equal to 0, which means x plus z is also equal to 0 when you divide by 3, right? So because this becomes 3x plus 3z equal to 0. So which means that what x is equal to minus z. Okay, so that is what you have for that equation. So our solution set will just be what? X is minus Z, Y is 0, and Z is a free variable. Okay, so that we can take Z out, so that will give us this. So that means the solution space for this is spanned by this vector. So which is one of the eigenvalues. So we've gotten one of the eigenvalues. Okay, we do this, we do this for the other eigenvalues to get all the other eigenvectors. Okay, and that will complete this problem. So let's move to the next one. The next one is when t is equal to 0. Okay, when t is 0. So let's move here. So when t is 0, what happens to this? Again, we'll look at this matrix. When t is 0, we now have 1, 2, 3, 1, 1, 1, 3, 2, 1. Now, the solution space of this is basically we have x plus 2y plus 3z equal to 0. We have x plus y plus z equal to 0. And we have 3x plus 2y plus z equal to 0. Again, we look at equation 1, 2, and 3. And we have to figure out the solution to this system. So one thing we can do is basically we can eliminate x from one of between equation 1 and 2. So what we'll do is we'll subtract equation 2 from equation 1. Okay. Right, when we do that, so combining this, we have x minus x, that will be 0. And the next one would be 2y minus y, that will be y. And then 3z minus z, that will be 2z, that will be equal to 0. Okay. Now, so this gives us what? Y equal to minus 2z. So we have a relationship between y and z. Well, what about, between equation, so let's also do the same thing for equation 1 and 3. So let's subtract, because we have 2y here, so we can use that to eliminate y. So let's subtract equation 1 from equation 3. Okay, when we do that, we'll have 3x minus x, that will be 2x, 2y minus y minus 2y, that will be 0. Then we have z minus 3z, that will be minus 2z. Equal to 0. So this effectively gives us 2x equal to 2z, which means x is equal to z. Okay, so we have this relationship between x, y, and z. So basically, z will be our free variable. The solution set would be x is z, y is minus 2z, and z is a free variable. So we can take z out, that will be 1 minus 2, 1. Okay, now you could solve this equation in a number of ways and you still come up with similar vector, depending on what you want to use as your free variable, and also depends on which equations you subtract from each other. Okay, now which means our solution space for this eigenvalue is spanned by this vector. Okay, this is the second eigenvector. And finally, we'll move to the last eigenvalue, which is 5, when t is 5. And what does that do for our matrix? So 1 minus 5, so I think we have minus 4 here. We have 1 minus 4, and we have minus 4. Okay, so this is what we have. Now, we need to solve this again. So this is minus 4x plus 2y plus 3z equal to 0. We have x minus 4y plus z equal to 0. And we have 3x plus 2y minus 4z equal to 0. Now, this is our equation 1, 2, and 3. Again, we look at how to eliminate some of the variables. And I think we can be very smart about this. So for example, we can eliminate y from equation 1 and 3 because we have 2y here and 2y here. So what we basically do is subtract both equations. So subtract, we subtract equation 1 from 3. Okay, now when you do that, what would we have? We have 3x minus 4x, that will be 7x. And then we have minus 2y minus 2y will be 0. Then we have minus 4z minus 3z, that will be minus 7z equal to 0. So this would give us x equal to z. Okay, so we have the first we have the first relationship. Now we can substitute x equal to z in any of the equations. So let's substitute this into the first equation. What would that give us? So substitute z here. We have minus x is z. So that's minus 4z plus 2y plus 3z equal to 0, which means 2y minus z equal to 0, which means z is equal to 2y. So we now have the relationship between among the three variables. So which means our solution set x is z. So if z is 2y, that means this will be 2y. So basically we are going to make y our free variable. So let's do that. You could also make z your free variable or your x your free variable. All of this would give us the same answer. So basically, if I make y my free variable, I'm smart enough to make this choice, and I'll show you the other route as well. Let's say we want to make z our free variable, we can also do that. So we know that our x is 2y, our y is a free variable, and our z is also 2y. So this will give us y 2, 1, 2. So this will be the third eigenvector. So the solution space for this eigenvalue will be spanned by this vector. Okay, and we're basically done here. So just want to show you. So what if we want to make z our free variable? So what happens is we know that what we need to write x and y in terms of z, right? So we know x is equal to z. We know y will be what? Z over 2. And we know z is a free variable, right? So that means your solution space, okay? Before we go back to the problem, your solution space would be x is z, y is z over 2, and z is just a free variable. So we can take z out, we have 1 over 2, 1. And if you want to make them, and if you want to make this, because we have a fraction, if you want to make it a whole number, just multiply it through by 2, and that means 2z would be 2, 1, 2, 1, 2, right? And this is just a variable, right? Another variable. 2z is just a variable, so it should still be spanned by this vector 2, 1, 2. All right. So which gives us the same solution as if you use y as your free variable. So now let's bring things together. We've gotten our eigenvalues. So the eigenvalues, we got them minus 2, 0, 5. Now the eigenvectors would be what? This set containing these vectors. So the first one we got for t minus 2, we have minus 1, 0, 1. The second one is for the eigenvalue 0 is 1 minus 2, 1. And the last one would be 2, 1, 2. Okay, 2, 1, 2. So this means this would be the set of bases for R cubed such that that transformation that we are looking at in this problem would be a diagonal matrix. And the diagonal matrix would be, so the matrix of transformation related to these bases for R cubed for both the domain and the range for this particular transformation will now be this. So we basically put the eigenvalues at the diagonals and everything else is 0. That's why we call it a diagonal matrix, right? And this is the solution to the problem. I hope you find this, although very tasking and also computationally intensive, this is a good example of how things can really get in an exam setting. So I hope this really helps. Make sure you subscribe to the channel if you haven't done that. Like this video, share among your friends in your own social media so that other students like you can benefit from this channel. And I'll see you guys in the next video.